Hello everyone, my name is Sai Strujan. I am from the data science second year and my topic is double hashing sort algorithm. Let's go into the topic. See here introduction. In the past few years, teachers have introducing several sorting algorithms to enhance the time complexity, space complexity, and stability. A double hashing methodology first collects statics about element distribution and then maps between elements of the array and indices based on the knowledge collected during the first hashing. Double hashing. Double hashing is a method for the resolving collision in the hash table. In a hash table, data items are stored in the array based on the hash code, which is computed using a hash function. However, two or more items may end up with the same hash code, resulting in the collision. The double hashing algorithm provides mechanism to handle such collisions. So double hashing is a main purpose is used to when they have the same hash code there will be a collision. Double hashing technique used by using we can use the collision, we can reduce the collision. The double hash sorting algorithm. The proposed sorting algorithm has phases: phase 1, first hashing, phase 2, second hashing, and phase 3. Sorting element in each slot. So these algorithms has phases are 3. So they are used for the sorting the algorithm. And first hashing, second hashing, sorting elements in each slot. Phase 1, first hashing. In the first hashing, the algorithm collects statistics about distribution of the elements in array. It then divides the array into blocks and calculates the number of elements in the each block. During this phase, the algorithm creates counter array. The following equation shows how the array is partitioned into 10 blocks. The 10th equal to max minus minimum plus 1 divided by 10. This is the equation to shows the array partition into 10 blocks. The algorithm performs the following equation on each element of the array to calculate the elements block and increment. Specified block in the mode of item slash the 10th. The counter array specified block plus increment. Phase 2, second hashing. The second hashing does not work blindly. Rather, it is used to statistics collected during the first hashing. Specifically, the algorithm gets each element's specified block and calculates its maximum and minimum. Max equal to specified block plus 1 into the 10th. Minimum equal to specified block into the 10th. It then maps the element to the virtual indexes in its specified block using the following equations. Float index equal to element minus minimum, max minus minimum. The index equal to index into counter array into specified block. So these two are the formulas. And the float index equal to element minus minimum and to max into minimum. Index equal to index into counter array and specified block. So if the block is a maximum, the block is B, the counter array B equal to 5. The algorithm maps E into the virtual index with 5 elements. At the end of the steps, the algorithm gets an array of the index However, some of these indexes are integer and some are the float point. Phase 3, sorting algorithm elements in each slot. In this phase, the algorithm contains a set of virtual indexes at the each block and the partition the indexes to the slot, with each slot containing one or more indexes that shares integer paths. Each slot is divided into two arrays. Equal array contains the integer indexes and its repeated values, and greater array contains the float indexes. It's the only array that should be sorted. So in this algorithm, the third phase, the algorithm contains a set of virtual indexes at each block and the partitions the indexes to the slot, with each slot containing one or more indexes that shares integer path. Each slot is divided into two arrays. Equal array contains the integer index and its repeated values, and great array contains float indexes. It's the only array that should be sorted. Flowchart. Let's see in the flowchart. First, start for I equal to 0 to I is greater than n less than n minus 1. If the false, it will be goes to the it will be skip the step. If it will be true, calculations calculate the block for the each item, the increment the counter and specified block. After next step, for I equal to 0 to I is less than n minus 1, if it is false, it goes skip the step, and if it is true, calculate the block of the each item by specified block and get maximum, minimum and count of the item in the specified block counter. Map of the each item to be scaled between 0 and add index to the slot. So if and next, for I equal to 0 to I is less than or minus 1, if it is false, it will be skipped into the next step, and if it is true, it will be goes to the insert equal array to the final position. Next, if the greater array size is greater than 1, if it is true, use quicksort to sort the greater array. If false, insert greater array to the final position. This is the end of the algorithm. Choose the two hash functions h1 and h2. Compute the initial hashing index using h1 key and % by the table size, where key is the item to be inserted and table size is the size of the hash table. If the slot at the initial hash index is empty, store the item there and return. If the slot is occupied, compute the secondary hash index using h2 key by the total size. Choose the two hash functions h1 and h2. Compute the initial hash function using h1 key by total size, where key is item inserted and table size of the hash table. If the slot at the initial hash index is empty, store the item there and return. If the slot is occupied, the compute the secondary hash index using h2 key table size. Probe the slot at the secondary hash index. If it is a empty, store the item there and return. If the slot at the secondary hash index is also occupied, compute a new secondary hash index using h2 key plus 1 by table size and probe the slot. Repeat the step 6 until a empty slot is found or until the algorithm has probed all slots in the hash table. Probe that slot, set the secondary hash index. If it is empty, store the items there and return. If the slots at the secondary hash index is also occupied, compute a new secondary hash index using h2 key plus 1 by table size and probe the slot. Repeat the step 6 until an empty slot is found or until the algorithm has probed all the slots in the hash table. Analysis of the double hash algorithm. The double hash algorithm is an effective method for resolving collisions in the hash table. Here are some key points regarding the analysis of the double hash algorithm. Time complexity. The first case of time complexity of the double hashing algorithm for inserting item is order of n, where n is the number of slots in the hash tables. This occurs when all slots in the hash tables are full and the algorithm has probed every slots before finding an empty one. However, in practice, the time complexity is much lower, typically order of 1 on average, as longer as the load factor of the hash table is not too high. So that the double hash algorithm is an effective method for resolving the collision in the hash tables. There are some key points regarding the analysis of the double hash algorithm. Time complexity. The worst case of the time complexity of double hashing algorithm for inserting an element item is order of n, where n is the number of slots in the hash tables. This occurs when all the slots in the hash table are full and the algorithm has to probe every slot before an empty one. However, in the practice, the time complexity much lower, the typically order of 1 on average, as longer as load factor of the hash table is not full. Hash function. The choice of the hash function is critical for the performance of the double hash algorithm. Ideally, the hash function should be uniformly distributed and independent of each other to minimize the chances of collision. The hash function should also be deterministic, meaning that the same key should always produce the same hash value. Load factor. The load factor for the hash table is the ratio of the number of items stored in the table to the total number of slots. A high load factor can be cause the hash table to become congested, leading to the longer probe sequence and slower performance. To maintain a good performance, it is important to choose an appropriate load factor and resize the hash table when necessary. Trade-offs. Double hashing provides a good balance between simplicity and effectiveness in resolving the collisions. Other collision resolution techniques such as chaining and open addressing have their own strengths and weaknesses, and the choice between them depends on the specific use case. Advantages. Effective performance. Double hashing provides efficient performance in the most cases. The algorithm uses the two hash functions to calculate the index of an element, which reduces the likelihood of the collisions and improves the overall efficiency of the algorithm. Good worst performance. Double hash guarantees that every element can be placed in the hash table without any collisions, make it an ideal choice when they're dealing with the worst case scenarios. The efficient performance of the double hashing provides the efficient performance in the most cases. The algorithm uses two hash functions to calculate the index of an element, which reduces the likelihood of the collisions and improves the overall efficiency of an algorithm. Good Worst case performance. Double hashing guarantees that every element can be replaced in the hash table without any collision, making it an ideal choice when the dealing with the worst case of scenarios. Easy to implement. Double hashing is easy to implement and does not require a lot of space. This makes a popular choice for the many applications suitable for a wide range of applications. Double hashing is used to various applications including database, network routers, compilers and more. It can be handle the large amount of data and provides a fast performance. Flexibility. The data hashing is a flexible algorithm that can be adjusted to suit specific requirements by adjusting the hash functions and the size of the hash table. It is possible to improve the performance of the algorithm for specific use cases. Disadvantages. Complexity. While doing the double hashing is generally easy to implement, it can be more complex than other hashing algorithms, particularly when multiple hash functions are used. This can make it more challenging to the debug and maintain. Poor performance with the bad hash functions. This efficiency of the double hashing dependency heavily on the quality of a hash functions used. The poorly designed the hash function can be lead to the large number of collisions which can slow down the algorithm performance. Large memory usage. In some cases, double hashing can be requires a large amount of memory, particularly if the hash table needs to be resized frequently to avoid the collisions. This can make the algorithm use suitable for the application with the limited memory resources. Limited order guarantee. While order double hashing provides a good worst case performance, it does not guarantee a specific order for the stored elements. These may be disadvantages for the every certain application that requires a specific order, not suitable for the certain data types. Double hashing is not also available suitable for the sorting certain types of data such as the strings, variable length and records. In such cases, other sorting algorithms may not be more appropriate. Conclusion. In the conclusion, the double hashing is a popularly sorting algorithm that offers several advantages, including efficient performance, goods, worst cases, performance, ease of the implementation, flexibility, and sustainability for a wide range of applications. However, it also some potential disadvantages, including the complexity, poor performance with bad hashing functions, large memory usage, limited order guarantee, and limited sustainability the order data types. Thank you.